Hi everyone, I'm Arpan. I'm a researcher at the University of British Columbia in Vancouver, Canada. In this video, I will give a brief primer on machine learning inference serving and a preview of related papers that are going to appear at the upcoming ATC and OSDI conferences. Cloud providers such as Microsoft, Amazon, IBM, Google, and many more have brought the power of machine learning to your fingertips today. And this has allowed application developers to seamlessly develop and deploy a variety of machine learning applications, be it for mobile devices, wearable devices, or IoT platforms. As a result, many web applications today extensively use machine learning, for example, activities like image recognition on social media platforms, music recognition on mobile phones, and health monitoring on smartphones all use some form or the other of machine learning. Now, at a very high level, machine learning as a service involves two different phases. In the training phase, cloud providers allow applications to train various machine learning models based on their data set. This is usually characterized by long-running batch operations for searching and fine-tuning the model weights and different hyperparameters, and typically there are no completion deadlines. On the other hand, in the prediction phase, which is also known as the inference phase, the trained models are then used to respond to specific queries from the end users. ML inference serving corresponds to the second problem, that is, the problem of computing predictions and responding to the prediction request from different users for different models in real time. In practice, although cloud providers support a variety of machine learning models such as for linear regression, cluster analysis, collaborative filtering, Bayesian inference, and even classification using deep neural network inference, a lot of research in the last couple of years has focused on deep neural networks, especially in the systems domain, because these are computationally intensive. The papers that I will cover today from ATC and OSDI in this video are no different in this regard. So let me start by explaining why is inference serving for deep neural networks at the cloud scale a difficult and a challenging problem. First of all, the inference serving system needs to support many different users and models at the same time. Different models may have different resource requirements, as you can see in the graph on the slide, and they might have different execution time and memory footprints as well. Moreover, the inference request for these models may arrive at different rates and with different regularity. For example, the workload can be periodic in nature, it can be bursty, it may have a sustained high request rate, or the request may arrive in a completely arbitrary fashion. In addition to supporting many models and lots of different types of workloads, the serving system also needs to satisfy service level objectives that demand each request to complete within a given deadline, such as 100 milliseconds. These service level objectives can be different for different applications, which further complicates the machine learning inference serving problem. Now, to meet all these requirements at the same time, the serving system often inevitably needs to use hardware accelerators like graphics processing units, tensor processing units, and FPGAs, because CPUs aren't fast enough to complete the inference computation for deep neural networks, which are often computationally expensive. However, accelerators are also costly and may consume a lot of power. The cloud provider therefore needs to manage the trade-off between cost and performance efficiently at runtime. The papers at ATC and OSDI this year target different aspects of this machine learning inference serving pipeline. The first paper, PET, which will appear at OSDI, explores how deep neural networks can be optimized for specific backends, thereby reducing their execution time and computation costs. Inference as a service, which will appear at ATC, explores the scheduling and model selection problem that the cloud providers face when dealing with lots of users and models and with different service level objectives. And finally, Palleon and Jumpstarter, which are also going to appear at ATC, look at improving the performance of machine learning inference in specific application domains like video processing and anomaly detection. I will now give a brief overview of the first three papers in the rest of this talk. PET is about optimizing tensor programs. You can consider tensor programs as the building blocks of deep neural networks, analogous to matrix multiplications or linear algebra operations. PET uses partially equivalent transformations and automated corrections in order to optimize these tensor programs. So what do I mean by this? Let's look at the goal of PET first. The goal is to optimize DNN executions for certain backends. And this is not new. Systems like Apache TVM compiler already do this today. For instance, Apache TVM starts from developer-friendly model representations like TensorFlow and Keras as inputs and compiles them down to an optimized executable for different types of backends like GPUs, CPUs, VTA, DSPs, etc. Another system, TensorRT, does something similar. It uses many different techniques like layer fusion, memory optimizations to produce an inference engine that is optimized for the GPU. However, all existing frameworks rely on equivalent transformations, which means that when a tensor program P initial is transformed into P1 and then P2 and then P3 and then finally into an optimized version, each step is sound and maintains the program semantics. PET takes a different approach. It uses partially equivalent transformations to generate the optimized program version. This allows it to explore a larger space of performance optimizations, and therefore the final program is much more efficient, but at the same time, it can lead to accuracy loss as well, because the program may not be same as the original program. PET therefore adds another step in the end, which automatically corrects all parts of the program that are the source of potential inaccuracies. The main contribution of PET is automatically exploring the space of partially equivalent transformations and correction techniques. Inf as a service solves a different problem. It focuses on the larger picture. That is, when there are lots of users with varying service level objectives, heterogeneous backends potentially, how should the cloud provider schedule all requests? So in the figure, for instance, when there are multiple backends, which backend should be used for which request, and which of the requests should be prioritized by the cloud scheduler? How should the models be cached in the host and device memory? Frameworks like TVM and PET that I just described earlier help reduce the execution time of a model on a specific backend. But what if there are different variants of this optimized model? One optimized for a single input, another optimized for a batch of 8 inputs, another for a batch of 16 inputs. Which of these should be used for inference? Should we wait for more user requests to arrive so that we can use the most efficient model? Inf as a service takes all these decisions at runtime based on the requirements specified with each individual request. These requirements are typically specified in the form of accuracy requirements, latency constraints, and service level objectives. Inf as a service also includes an autoscaler component, which automatically increases or decreases the number and the type of backends provisioned for specific models based on the workload. Finally, unlike PET and Inf as a service, Palleon looks specifically at the video processing problem. The video processing problem essentially involves running inference continuously on different video frames. The focus of this paper is on video processing for cloud-backed mobile platforms, which means that the power consumption is an important performance metric. So let's look at the ImageNet dataset first, which is widely used for image classification tasks, and therefore models trained on ImageNet are also useful for video processing. This dataset contains more than 1 million images belonging to 1,000 different classes. On the right-hand side, there is a list of models obtained from the Keras website summarizing the size and the accuracy of different models when trained using the ImageNet dataset. So as you can see, most of these models have a fairly large memory footprint in the context of mobile and edge platforms. As a result, using these models for inference is often prohibitive. Also, since latency constraints are extremely tight, offloading the problem to the cloud domain is not always an alternative. It should only be sparingly used. Also, notice that unfortunately, the smaller models have relatively lower accuracy as shown in the table. Therefore, in order to get around these constraints, Palleon observes that video frames actually have temporal locality. As a result, the classification output is actually highly skewed in favor of only a small number of classes at any period of time. And all the 1,000 classes which are used for training are actually rarely observed. So if the class queue can be accurately determined, a more compact model can be trained and used during inference instead of generic models that are listed in the table. Palleon therefore dynamically detects the class queue and shifts in the class queue as well in the video processing pipeline at runtime and adapts the models that are used for inference, thereby saving a lot on the power usage of the mobile platform. So to summarize, all these papers will be presented on Wednesday, July 14th, in the first session at OSDI and in the third session at ATC. Jumpstarter and FT-pipe are two other related papers that I did not discuss due to time constraints. But like Palleon, Jumpstarter also focuses on a specific application, anomaly detection in this case, but actually it proposes to use signal processing instead of machine learning. FT-pipe is a system that does not focus on inference, but on training rather. It focuses on the training of giant models on multiple GPUs in a pipeline fashion. So that's it from me. Thank you for listening and hope to see you all at the conference.